Okay, welcome back, everybody. I would like to continue with chapter 12. We'll get that done today. And then if you have any questions afterwards, I'll open up the rest of the time we have. I won't jump into 13. I'll jump into 13 on Tuesday. Okay. Anyway, let me share the screen. We have been talking about the concept of the mole. Okay, and you're going to see here that that concept of the mole, well, point number one is simply a number. Okay, just that's all it is, just a simple number. It just happens to be a very large number. 6.02 times 10 to the 23rd is 602 6 trillion. That's a lot of zeros there, right? Humongous number. All right, so, and to give you kind of an idea of perspective of how large this number is if you were to get 1 mole of softballs, which are probably somewhere like 3 or 4 inches in diameter, a softball, if we have 1 mole of softballs, we will have enough softballs to be the size of the Earth, okay? And thing is that because the atoms are so tiny, these numbers are just amazing with respect to how many atoms we're talking about. And I'll give you some examples here in a bit. All right, now, with respect to the atomic weights on the periodic table, okay, we talked about these a while back, where we would look at, say, for carbon, that the number below the symbol, okay, was a decimal number, okay, 12.01, which at the time we really didn't talk about the units there, but the units for the atomic weight are in grams per mole, okay, grams per mole. Those are the units of all these atomic weights. Now, what that tells you is this, that, for example, if you were to weigh out 12.01 grams of carbon, it would be equal to 1 mole of carbon, okay? And if I were to weigh out 14.01 grams of nitrogen, just atoms of nitrogen, we would, that would weigh 14.01. Now, here's something also important to remember. Remember, we had the diatomic elements, okay? We had 7 of them. They were diatomic. So remember here, when you're asked the question, we're going to learn about what's called the molar mass. And basically the molar mass is the sum of the atomic weights of all the atoms in that compound. And since we know that all these, like nitrogen and oxygen, are diatomic, then their molar mass is simply twice the atomic weight. So oxygen, it would be 32 grams per mole, unless the question asks for the atomic weight for 1 atom of oxygen, then it will be 16. Okay, so we double the atomic weight for all of the 7 diatomic elements that we have. Okay, remember that. Have no fear of ice cold beverage. The 7, you may go back and refresh your memory. All right, so the one thing they all have in common here is that everybody equals to 1 mole. Okay, so phosphorus, I weigh out 30.97 grams of phosphorus, we got 1 mole. Okay, and having 1 mole means that I have 6.02 times 10 to the 23rd atoms. Okay, now what I do is I equate that to eggs, and you might be thinking, all right, what is eggs going to do with chemistry here? Well, I'm glad you asked. Let's do some examples. Okay, so we all know about the concept of a dozen, okay, a 12. So let's say, for example, that we looked at some small eggs, and for argument's sake, this is just argument's sake, a dozen small eggs weigh 100 grams per dozen, okay? Medium eggs, we take a dozen of medium eggs, and we'll just double that, and that weighs 200 grams per dozen, okay? And then large, we'll just continue and just set a factor of 100, so 300 grams per dozen. Now, what they all have in common is they have 12 or a dozen eggs, okay? We know that 1 dozen is equal to 12, okay? And so if somebody were to ask you, all right, if I have 2 dozen small eggs, how much would they weigh? Okay. What if I have 2 dozen small eggs? Okay. What would be the weight of 2 dozen small eggs? What would you say? What do you got? 24? No. We have 2 dozen small eggs, which yes, which is 24. You're correct, and Karen, you have 24. But since 1 dozen weighs 100 grams, then 2 dozen would weigh 200 grams, like Samantha put there. Okay. And if I had 3 dozen, I would have 300 grams. Okay. So we get that concept, right? Now let's go the other direction. What if I had half a dozen eggs of small eggs? We're just going to work with the small ones. Half a dozen small eggs. What would its weight be? Exactly 50 grams. Because if 12 of the small eggs weigh 100 grams, obviously 6 would weigh half of that. Okay. Excuse me. And so the concept here, I want you to continue with it when we start talking about atomic weights. And we're talking about the molar mass. So for example, if we go back to carbon, okay, carbon has an atomic weight of 12.01 grams per mole. Okay. And so if I take out 1 mole, it would weigh 12.01 grams. Okay. Well, how many atoms would that equate to? 1 mole would equate to how many atoms? Well, that would be Avogadro's number. Atoms of carbon. Okay. Just like 1 dozen or 12 eggs would equal 100 grams. In the example we did here with the eggs, 1 mole or 6.02 times 10 to the 23rd atoms of carbon would weigh 12.0 grams. And if I weighed out 6 grams, 6 grams of carbon, I would have half a mole, right? Because a full mole weighs 12.01. Well, half of that would be half a mole, which would be half of Avogadro's number, okay? Just like we were using the examples up here with the dozen eggs and so forth. We grasp that because that's a small number. So now when we move over to Avogadro's number, it's the same concept, it just happens to be a larger number, that's all, okay? All right, so you can go to any element on the periodic table and if ever asked, how many grams is 1 mole of boron or 1 mole of sodium weigh? Well, it weighs 22.99 grams. Okay, just like if 12.01 grams would equate 1 mole. They both, in both cases, have 6.02 times 10 to the 23rd atoms, each of carbon and sodium, respectively. Okay. All right. So again, 1 mole is nothing more than a number, 6.02 times 10 to the 23rd entities or units. And it could be anything you want to count. But in chemistry, we're generally counting atoms, we're counting ions or molecules or formula units. It could be bananas, oranges, whatever you want to count. It's just a number, okay? Nothing magical. And furthermore, this number here is a whole number, okay? Just like a dozen is 12, it's an exact number. This is a whole number. So this number wouldn't be used with respect to your final sig figs, your final significant figures, okay? Because it's a whole number, it's an exact number. All right, so with respect to molar mass, and that's when we're talking about the atoms themselves, it's simply their atomic weight. So if you're ever asked, how many grams does equate to 1 mole of carbon? Well, you just look up its atomic weight, and that is 12.01 grams per mole. Gold, 196.97, and sodium, like we had earlier, 22.99 grams. All of these have the same quantity of atoms, 6.02 times 10 to the 23rd atoms. It's Avogadro's number, okay? All right, so that's the molar mass for simply the elements. A lot of times we have, quite a few number of times, we have the molar mass for a compound. Now, up to this point, remember, we have been putting together, given the name, we have been putting together the compounds. And recall that I've been telling you, when we're putting together the ionic compounds, we first determine the ions that each one has, the cation and the anion, then we put them together with the right ratio so they cancel each other out, okay? So here we have an example of barium hydroxide. So no different than what we've been doing in the past. We have the name of the compound, and what we're asked is to determine the molar mass for barium hydroxide. The molar mass is nothing more than the atomic weights, the total atomic weights of all of the atoms in that formula. That's it, okay? With the units of grams per mole. And so before we can determine the atoms and which ones, we ought to write the formula so we're given the name. Notice it's an anionic compound, barium hydroxide. And so what we got to do first is write them in ion form. So we got barium, which is a +2 metal, okay? Ionic form is a it's a group 2A metal. So in ionic form, it is a +2 charge. The hydroxides are the polyatomic ions. The OH, the base, remember the bases, we talked about these, and they each have a negative charge, 1. And therefore, we need 2 hydroxides for every +2 of the barium. So the formula is Ba parentheses OH subscript 2, okay? So we must, from the formula, from the name, write the formula before we can determine the molar mass. Now, once we've done that, we did some exercises with formulas, and at that time we didn't say what they were. We just said, okay, how many hydrogens you have here, how many this, how many that. We do the same thing here. We got 1 barium, okay? We got 2 oxygens and 2 hydrogens. Total 5 elements in the formula for barium hydroxide. Now we go to the periodic table and we look up the atomic weights for barium, atomic weights for oxygen times 2, because there's 2 oxygens, and then the atomic weight for hydrogen times 2, because there's 2 hydrogens. And we tally all that up, and we end up with the following, okay? That is 137.33. That is the atomic weight for the barium. The oxygen has an atomic weight of 16. There are 2 of them in the formula. Okay, so it's 2 times 16. The hydrogen, each hydrogen has an atomic weight of 101. Okay, times 2, because there's 2 of them. Okay, and when we tally all that up, we get a grand total of 171.35 grams per mole. That is the molar mass for barium hydroxide. Okay, note something. This is a ratio, just like the ratios we've been doing and working with way back when we're doing the conversion factors. Okay, 1 inch is equal to 2.54 centimeters. That was a ratio that we can write centimeters in the numerator or in the denominator. This is the same thing. So I can write the molar mass with grams in the numerator, numerator, and 1 mole in the denominator, okay? Or I can simply invert it. Okay. Now, why I want to do this, put them in this form, is because this is how I'm going to use my numbers to convert from one unit to another. So if I'm given X number of moles and I need to figure out the number of grams, X moles, I'm going to use the one on the right because moles cancel and I end up with grams. If I'm given X grams of a material, in this case, barium hydroxide, I'm going to use the one on the bottom because my grams cancel, leaving me with moles, okay? And it's just no different than how we did the conversion factor. Okay. All right. And these ratios are related, what we're doing here are related to the balance in the equation and those particular ratios with respect to reactants and products, okay? Because here's the deal. If I react compound A with compound B, and I have X number of grams of A, and I have X number, I need to determine X number of grams of B, I cannot go from grams of A to grams of B directly. What I need to do is I need to find a common unit for these. And the common unit in chemistry with respect to calculations is moles. So if I have X grams of compound X, I need to convert that to moles of compound X. And then from the moles of compound X and then the ratio of the balanced chemical equation, that would get me to moles of whatever compound I'm looking for. And from the moles of the compound that I'm looking for, and given its molar mass, I can now convert to grams of whatever compound I'm looking for. The intermediate unit is moles. And that's why the moles is an important concept that we need to grasp and how to convert from grams to moles and moles to grams. Okay. All right. So that is the molar mass for barium hydroxide. Now, Avogadro's number is no different than the others with respect to ratios. Avogadro number is also a ratio, okay? And I can write it like this on the left, or I can write it what's on the right. Which one I use depends on which units I'm looking for, okay? Remember how we did the conversion factors? You know, when I get from point A to point B, I set up my conversion factor such that what I'm given cancels out to look for a new unit. Okay, this is no different. Okay, so here the question asked is how many calcium atoms are in 0.25 moles of calcium? They want to know how many atoms are there in moles of calcium. Notice we're not dealing with grams yet. We're working with just the moles and atoms. All right, so we write down what we're given, just like we've done before. We're given 0.25 moles of calcium, okay? And then we write down what we're looking for. Well, what are we looking for? The question says, how many atoms of calcium does that correspond to? So obviously we're going to need a factor here at 1, just looking at the units, I haven't even thrown in numbers. I want it so I got moles in the denominator. Why? Because I want moles to cancel when I multiply. And then I want in the numerator atoms, okay? Therefore, I am using the conversion factor on the left-hand side. 6.02 times 10 to the 23rd divided by 1 mole. Okay. When I set that up, you notice that I end up with atoms in the units, and that's where I'm trying to get to. Okay. All right. So you should have something like that. So a quarter of a mole. The other aspect too is think about what the questions are. Excuse me. Think about the questions and the mathematics you're doing. You're taking a quarter of a mole, okay? And that means that since you're starting with a quarter of a mole, that I should have a quarter of Avogadro's number, which this is 1.51 times 10 to the 23rd, okay? Okay. So that number looks reasonable as far as the mathematics involved. So always consider, look at the mathematics, look at your answer, and be like, does it make sense? All right, in this particular example, they're asking you to calculate the number of moles if I have 3.75 times 10 to the 27 molecules of oxygen gas, all right? And I need to know how many moles that represents of O2. Okay, well, that means that I need Avogadro's number in this format with a 6.02 times 10 to the 23rd molecules per mole. The mole in the numerator, Avogadro's number in the denominator. Okay, molecules cancel with O2, leaving me with units of moles, which is what the question asks for. And so now you got to remember how to use your calculator scientific notation. So you take 3.75 times 10 to the 27 divided by 6.02 times 10 to the 23rd. Then you do the math and you end up with 6,230 molecules. Excuse me, moles. So 3.75 times 10 to the 27 molecules of oxygen corresponds to a little bit over 6,230 moles of oxygen. Quite a bit. Okay. All right. So in this exercise, what we're doing here is we are going to take grams and convert that to moles. Okay. What we just finished doing was to take moles and convert that to molecules, or molecules and convert that to moles. Okay. But like I stated, moles is our unification unit, if you will. That is the unit that I can go from compound A to compound B. The only way I can do that is I need to convert compound A into moles, and then from that, go into the moles of compound B. Okay. Now keep in mind, the molar mass has the units of grams per mole. So I can write grams per mole or moles per gram. Okay. Which one I use depends on the question. All right. Here is actually how many grams is 1.667 moles of oxygen gas. Okay, well, first point, we're talking about oxygen gas. Now, oxygen atoms, oxygen gas. So we need the molar mass for oxygen gas. And we know that oxygen gas is diatomic. Each oxygen has its atomic weight is 16 for each oxygen. So if we have two of them, the molar mass is 32.0 grams per mole for oxygen. Okay. All right, so what we're looking for is grams, and we're starting with moles. So we write down, excuse me 1 second. Write down what we're given, 1.667 moles of O2, okay? and we're striving for grams of O2. So obviously we're going to have a conversion factor that we want to get rid of moles. So we put moles in the denominator. Okay, so it's basically 1 mole, and then we want grams in the numerator, which goes on top. Okay, so moles of O2 cancel out, giving us grams of O2. Okay, so you see how we set that up? All right. And we end up with 53.34 grams of oxygen. Okay. And that's going from moles to grams. Notice something. When you start with moles and you need to get to grams, guess what? You're multiplying by the molar mass. Okay? Think about that for a second to help you out. I'm given moles and I need to get to grams. I am multiplying by the molar mass. MM. Molar mass. Okay? Moles times the molar mass gives me grams. All right, here we're asked to figure out how many moles is 45 grams of silver. Okay, so we need silver. It's a atomic weight, which is silver is 107.87 grams per mole. Okay. So how many moles is the question? And we start off with 45 grams. So we've got 45 grams of silver. Okay. And we're looking for moles of silver. So therefore, we need our atomic weight with grams in the denominator and moles on top. So that's 1. And that's 107.87. So grams cancel, leaving us with units of moles of silver, which is what we're looking for. Okay. All right, and that becomes 4.42 moles of silver. All right, how many grams is 0.0554 moles of water? Right. Well, what we need first is the formula of water, which we all know is H2O. Okay. Oxygen brings in 16. We need a molar mass. Oxygen brings in 1600. Each hydrogen brings in 1.01. So we got 2 of them. So it's a total of 2.02. So the molar mass for water is 18.02 grams per mole. That is the molar mass for water. All right, we're looking for grams. Write down what we're given, 0.055 for moles of water, H2O. Okay, we're looking for grams of H2O. So we set up our molar mass with grams on top, which is 18.02 over 1 mole. Okay, moles cancel. We got units or grams left over. So we're good to go. Now it's a matter of you doing the mathematics on your calculator, and you should end up with the following. All right. So almost 1 gram, so 0.998 grams of water. It calculates to have 0.0554 moles of H2O. Okay. All right. Now here's one that we're looking for. We want to look for potassium. Potassium, we're looking for grams. We're dealing with potassium. So let's write down what we know. We know that the atomic weight for potassium is on the periodic table, and that is 39.10 grams per mole. Okay. And then Avogadro's number, we're going to need that because we're dealing with atoms and we're going to get to grams. Okay. Notice that we have atoms and we got to get unit wise to grams. Okay. So before we can do that, we need to get through moles first before we can do anything. So we got to get from atoms to moles and from moles to grams, because we cannot go directly from atoms to grams. So moles is our common factor. Okay. All right, so let's write down what we got. And we have 4.75 times 10 to the 16 atoms. Okay, and we need to get to grams of potassium, atoms of potassium. So obviously the first one would be Avogadro's number. Okay, because we need to get from atoms to grams, we need to go through moles. And so we need Avogadro's number to get us out of atoms. Okay, 6.02 times 10 to the 23rd atoms. Notice my atoms cancel, leaving me with moles of potassium. Okay, well, I've got to get to grams, and to get to grams, I need the atomic weight for potassium, which on the periodic table, 39.10 grams per 1 mole. Notice the moles cancel, leaving me with units of grams, which is what we're striving for. So I'm taking 4.75 times 10 to the 16, dividing it by Avogadro's number, and then multiplying it by 39.10. Okay. And once you do that, you should end up with 3.09 times 10 to the negative 6 grams. Yeah, here's a number that maybe should kind of sit there and say, okay, we got that number of atoms of potassium. That's a big number, 4.75 times 10 to the 16. But after everything's said and done, that only weighs 3.09 times 10 to the 6. We got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. We've got too many. One, 2, 3, 4, 5. Messed it up again. And no zeros. Yeah, 1, 0. So look how small that weight is. Okay. We have nothing that in a typical lab that can weigh that small amount. That's an extremely small amount. And yet, look at the quantity of atoms that it has. 4.75 times 10 to the 16. Granted, it's not Avogadro's number, 10 to the 23rd, but it is still very, very large. Okay. And having this large number of atoms, you still have a very small weight. So that should give you hopefully some perspective as to how small these atoms are. Extremely, extremely tiny. All right, so that is an example of getting from grams to moles. Now, we need to do that because, like I stated, when in the quote real world in calculations, be it in the lab, be it in the industrial plant, you still go through the same calculations. It's just that the numbers can be bigger if you're doing an industrial plant here. Okay, but the same process it occurs. But we need to get to moles. So if you're given grams, you gotta get to moles. All right. Which brings us to what is called the molar volume. Now, way back when we were talking about the properties of solids, liquids, and gases, we stated that the gases had no set volume. Okay. And I believe I pretty much stated that at this point in time, that is a true statement, but it will change later down the road. But here we are. Okay. Now, under certain conditions and only certain conditions that are called STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere. Okay, 0 degrees Celsius, which is freezing, and in 1 atmosphere, which is approximately where we're at right now, 1 atmosphere of pressure. Under these conditions, gases have a known volume, specifically 1 mole of gases. So if we look at the gas here where we have hydrogen, fluorine, ammonia, xenon, and methane, all of them are gases. We all have 1 mole of these. Obviously, since we have 1 mole of every gas, we're going to have the same number, just like if you have 1 dozen of 3 different sizes of eggs, you still got 12. Okay. Well, the number of molecules for the 1 mole is Avogadro's number, 6.02 times 10 to the 23rd. The molar mass obviously is going to be different, okay? Because hydrogen is a much smaller atom than fluorine, than, so on and so forth. So the molar mass is the sum of the atoms for that formula. So hydrogen, there's 2 hydrogens. Total molar mass of 2.02 times 10, 2.02 grams per mole. Okay. Xenon, the biggest one here, has 131.29 grams per mole. Okay. Now, under those conditions only, those gases have a volume for every mole, a volume of 22.4 liters per mole. Okay. Let me repeat that. Under those conditions only, STP at 0 degrees and 1 atmosphere, 1 mole of gas occupies a volume of 22.4 liters. And now we have another ratio that we can use to our advantage, where we can take liters and convert them to moles, okay? Because 22.4 liters per mole can be written like that, or it can be written inverted, 1 mole over 22.4 liters. All right. So under these conditions, only 0 degrees and 1 atmosphere. So here's our factor. So we can write it as 22.4 liters over 1 mole, or 1 mole gas, whichever it may be, over 22.4 liters. And as we do for any ratio, which one we use depends on the question and what units we are looking for. All right, for example, a point about these habit calculations. 1, they're either going to state that they are in STP conditions, which is great, okay? Because only under those conditions can you use the 22.4 per mole, 22.4 liter per mole relationship. So they may spell it out STP, or they may say 0 degrees and in 1 atmosphere, okay? Which is inferring, it's telling you it's STP. Then you can use that relationship. If they don't mention temperature and pressure at all, then there's nothing you can do as far as calculations. Okay, and basically you can't calculate, you don't have enough information. All right, so here it says, what is the volume of 1.25 moles of argon gas at STP? All right, so we write down what we're given, 1.25 moles. Okay, right away, that should give you a little hint here as far as the magnitude of your answer, because you know that in 1 mole, it occupies 22.4, and you got a 0.25, a little extra. So your volume is going to be a little bit greater than 22.4. If your number's less than 22.4 or at 22.4, then you did an error someplace, okay? And so we were looking for volume. Yes, all right, so here we are. And we put in 22.4 liters in numerator, 1 mole in denominator. Moles cancel, leaving us with liters, so you just do the math. And that answer is 28.0 liters of gas is equivalent to 1.25 moles of argon gas at STP only. Okay. Next one is, how many moles is 30.4 liters of O2 gas? How many moles of O2? Okay, at STP, so we can continue with that relationship. We got 1 mole over 22.4 liters. Liters cancel. Okay, and you can do the math, and you can see that you're going to be, the fact that you are at 30.24 liters should tell you that your answer is definitely going to be greater than 1, because you know that at 1, you're going to that occupies 22.4 liters at 1 mole. Okay, so you are a little bit greater, a little bit less than 8 liters more. So your moles should be a little bit greater than 1. Yep, 1.36. Okay. Now notice here, with respect to sig figs, the 22.4 liter is a measurement, and therefore could play a factor in determining your number of sig figs. Okay, so don't forget that. Remember, any measurement is not exact number, so it could play a factor in your sig figs. The next one here, they're asking you for a couple of things. They're asking you for the mass of 4.5 liters of chlorine gas. Okay, so given that you're asking for the mass, here's the deal. You're going from mass in grams to liters. Okay, you can't go directly. You have to go through mole. Okay, and then chlorine gas is diatomic, so it's Cl2. Okay, so chlorine is 35.45. So times 2 gives you the molar mass for chlorine. Okay. And you should end up with the following. Okay. The first factor is the factor that cancels the liters out and gets us into moles of chlorine gas. Okay. From moles of chlorine gas, we use the molar mass of chlorine, okay, to give us grams, because moles cancel, leaving us with grams of chlorine gas. So 4.5 liters of chlorine gas equate to 14.2 grams of chlorine gas. Okay. So notice we have 2 factors here. In general, when we start doing a lot of these calculations, especially with the chemical reactions, you're going to end up with at the minimum 3 conversion factors. Okay. And all you got to do is keep track of your units. That's how you're setting these up. The other factor, keep track of your units, and remember that I can't go from grams to liters directly. I got to go through moles. Okay, I got to go through my common factor of moles. And this is this flow chart for you, which will help you see the full picture, okay? You can see here that our common factor is moles. All right, so if I'm given a problem in grams, what I need is the molar mass to convert the grams to moles, okay? Once I do that, using Avogadro's number, I can go from moles to atoms or ions or molecules or formulas, okay? If I'm at STP and I use this relationship of 22 liters per mass, 22.4 liters per mole, I can go to volume, okay? So I can go from here to here. Now I'm using double arrows because what that means is you can go both directions. You can start at volume and work your way back to grams, okay? Or work your way back to atoms, okay? But you can't do any of that unless you go through moles. That is important. You got to get to moles. Now we're going to have another flow chart down the road that's going to incorporate more information. And I can tell you right now, with respect to these type of calculations, print out the flow chart. That flow chart will help you, at least in the beginning, see the full picture. Because I know that these chemical equations, one could easily get lost in them and lose sight of how are you going to calculate, okay? But if you use the flow chart and just follow it through, okay, you shouldn't have a problem. It's determining what you need to do to get to the units or to the answer you're trying to get to. All right, so for example, here they're asking you, how many grams does 17.35 liters of neon gas mass? So basically, if I have 17.35 liters of neon gas, what is its mass? If you are at STP. So here's the thing. All right. We are at STP. We can write down 22.4 liters. Jesus. The fact that we are at STP tells you we can use this ratio. Okay. For mole. All right. So write down what we are given. And I also wrote down what the answer is. But anyway, we're given 13.35 liters and we need to get 2 grams of neon. Okay. So in order to do that, we're at liters and where are we? Right here? We are in liters. Right. Oh, I don't know why this thing's not working on me here. We are in liters and we got to get to grams right here. Okay, that's what we're doing. And well, to do that, we got to use that factor to get us into moles, and then we're going to need the molar mass to get us into grams. And so that's what I mean by using this flow chart to help you keep track of how you set that up. All right, so the first one is write down what we're given, 17.35 liters, okay? And we're trying to get 2 grams, and the answer is there, but we got factors. Well, the first factor, since we are at STP, the first factor is the 1 mole is equal to 22.4 liters, okay? That gets us out of liters with respect to units and puts us in the moles, okay? And from the moles, we need now the molar mass, atomic weight of neon, which is 20.18 grams. And our moles cancel, leaving us with liters, okay? This is no different than what we got right here, okay? we started off with volume, and we're going in that direction to figure out the grams. We need this relationship and the molar mass, okay, to get us to grams. And there you go. Okay, from that point, there's a second part of that question. It's asking you, oh, how many atoms is this? Okay. But if I have 17.35 liters, how many atoms does that correspond to? Well, let's look at the flow chart. Okay, the flow chart, we are here. And now we want to know how many atoms. So we're going to this direction, we're going in that direction right there. We went to the left, but now we're going to the right. So again, we still need the 22.4 liters per mole. And then we need Avogadro's number to get us to the number of atoms. Okay, so we write down what we're given, 17.35 liters, 4.66 times 10 to the 23rd atoms is our answer. Excuse me 1 second. There's something floating around here making me want to sneeze. All right, so notice our liters cancel, moles cancel, leaving us with the units of atoms, okay? So when these type of reactions here, these type of calculations, rely on that flow chart to help you go through whichever direction you need to go. Because I can't overemphasize the aid in that flow chart, because, and the other aspect is too, is the follows, is that we can go from grams to atoms, okay, from grams to volume, okay, and from every direction here. So if we got in volume, we can go to atoms. When we're in volume, we go to grams. But the point is, you have to go through moles. Okay, moles is our factor that is common to everybody. Okay. All right, well, with that information there, okay, these type of calculations are really no different with respect to setting them up like we did with the conversion factors, okay? Using the factor label method, basically keep track of your units and set that up properly. Making sure units cancel out and so forth. All right, now with respect to density, we had talked about this before, where you actually measure something out and determine its volume and you figure its density. Well, we can do this with respect, also do it to gases at STP, only at STP, because and we don't have to measure anything, because we know the molar mass of the gas that you're working with, and we know the molar volume, which is 22.4 liters. So we can calculate the density of ammonia gas at STP, because the molar mass of ammonia is 17.04 grams per mole, and the molar volume for any gas at STP is 22.4 liters per mole. So when you do that, units cancel out, you end up with units of grams per liter, which is a density unit, okay? All right, now, this brings us to the percent composition. In the process of determining the molar mass for the compound, what we did is, obviously, we wrote the formula. We determined the formula. Remember, we did the barium hydroxide. After writing the formula for that compound, we had to figure out the molar mass. We added up all the contributions of all the atoms in that formula. Okay, now we're going to take it one step further. We can take the individual contribution of a specific atom or element and divide it by the total molar mass, and then multiply it by 100. And what that does, it gives us the percent composition of that element within that compound. Okay. For example, we all know that H2O has the formula H2O for water, right? So we know that I went through the exercise where I determined the molar mass for water because there's one oxygen, two hydrogens. Its molar mass is 18.02 grams per mole. Okay. The contribution for hydrogen is 2.02. Each hydrogen brings in 1.01, so it's a total of 2.02 for the hydrogens. Divided by the whole, which is 18.02, okay? The part over the whole, the part is the hydrogen, okay? Divided by the whole, which is the whole molar mass of the molecule, times 100 gives you the percent composition for hydrogen in water, which in this case is 11.2%. You do the same for oxygen. There's one oxygen at 16 divided by 18.02 times 100. Oxygen brings in 88.8% the percent composition for oxygen in the formula of H2O. And we do this in the real life too, in the lab, especially in organic chemistry when we're making new compounds. We clean them up real well. Based on other equipment, scientific testing, we know the structure, or at least have an idea of the structure, and then we take a sample out and do a calculation for the percent composition for all the elements. Send a sample out, and then if it comes back and it matches what we calculate, it adds more data to verify that yes, we made a particular compound that we were striving to make. So hydrogen for water consists of 11%, and that is true for water, hydrogen and water here in Arizona or on the North Pole, or for that matter, on another planet. Okay, that's the composition of water. All right, so now we have an example of how to calculate the percent composition for, here we go, TNT. Anybody know what TNT is? Yeah. Yeah, you're right. It's a Looney Tune explosive. That's correct, Samantha. Specifically, it's dynamite. It is an explosive. Let me take a chance here. Anybody know who discovered TNT? It's a very important chemical. It opened a lot of industrial things that we can do with it, good and bad. Okay. I'll give you a hint. Every year there's a prize named after him. Anybody want to take a guess? In fact, they give a prize in medicine, they give a prize in chemistry, in physics, in literature. It's a nice little prize. Nobel, you're correct. Anna Karen. Nobel is attributed to synthesizing TNT, which is quite an accomplishment because it's so unpredictable and sensitive. And I know this is beyond the scope of Chem 130, but I'm just going to show you what it is structurally. It's a 6-member ring, hexagon ring, with alternating double bonds and single bonds. And there are 3 nitro compounds, nitro groups around it. And because And this is toluene, then there's a CH group there. I know this is beyond the scope, but the reason is so explosive is because the nature, the beast of these groups here, the nitro groups. Putting the first two on when you synthesize it, not too bad of a challenge. Just putting that third one in, that things can go array. All right, just a side note there. So here they're asking you to find the percent composition. The point here is, obviously you may not know what the compound is, but you know how to count the atoms, okay? In that formula, you know where to get the atomic weights for each of the atoms, and you know how to multiply, and you know how to add, okay? Or nothing else, you know how to push the buttons in the calculator, right? Okay, so let's run through the numbers. So do use the atomic weights for the from our periodic table. There are other atomic weights, not much different from ours. They may add more digits to it. The problem is this, is the answers on Canvas are based on the atomic weights on the periodic table we hand out. So if you use a different number, maybe an additional significant figure or something, your answer could be slightly off, which, Canvas doesn't understand a slightly off number and will count you wrong, okay? Having said all that, if you know 100% yet your number is correct, I have no problem. Send me an email, tell me what problem it is, I'll look it up. And if you're not way out in left field, I'll say, yeah, I have no problem giving you credit, okay? If you're only off like 0.01 or something like that. All right, so let's add up. There's 7 carbons. Each one weighs, atomic mass is 12.01. So I have a total of 84.07 grams per mole for the carbons. There are 5 hydrogens, each at 101. That's a total of 505. 3 nitrogens at 1401, giving you a total of 4203 for all the nitrogens. And then there are 6 oxygens at 16 apiece. It's a total of 96. So the total molar mass for TNT, trinitropentane, is 227.15 grams per mole. Now, let me ask you this. How many atoms, no, how many molecules of TNT would I have if I weigh out 227.15 grams? How many individual molecules would I have if I weigh out 227.15 grams of TNT? Okay. Anybody taking a shot at that? Not a trick question. Okay, let me restate it again. If I weigh out 227.15 grams of TNT, how many individual molecules of TNT would I have? Okay, well, how many moles would I have? Let me start with that. How many moles of TNT would I have if I weighed out 227.14 grams? Okay, well, let me use an analogy. Remember earlier when we were talking about the small eggs? And I said, well, let's just say, for example, there's 100 grams per dozen. Okay. Now, if I weigh out 100 grams of small eggs, how many dozen would I have? One dozen, exactly. How many eggs would I have? 12, exactly, right? Now, let me go back to this number here. if I weighed out 227.15 grams of TNT, how many moles would I have? Remember, the mole is the chemist's dozen. How many moles would I have? Look at the units of the atomic weight. What did it say? No, not 2.27. Look at the units, grams per mole. Like right here in the small eggs, it said 100 grams per dozen. So if I had 1 dozen, okay, if I have 1 dozen eggs, they're going to weigh 100 grams. If I have 1 mole of TNT, it's going to weigh 227.15 grams. Okay. So I'm asking the opposite direction. If I weigh out 227.15 grams of TNT, how many moles do I have? No, not 18.92. 1 mole. Remember water, H2O, it was 18.02 grams per mole. If I weigh out 18.02 grams of water, I have 1 mole. If I weigh out 227.15 grams of TNT, guess what? I have 1 mole. Okay. And in both cases, how many individual atoms or molecules would I have? 6.02 times 10 to the 23rd. Okay. All right. All right, so that is a total molar mass for TNT. Now to calculate the percent composition, we take the individual atoms and their total mass and divide it by the total molar mass. So we got 84.07 divided by 227.15, 5.05, 42.03, and 96.00, all divided by the total molar mass multiplied by 100, okay? And you end up with the percent composition. So TNT consists of 37.01% carbon, 2.22% hydrogen, 18.50% nitrogen, and 42.26% oxygen, okay? And you can do this for any molecule that's out there. All you need is the formula, okay? All you need is the formula, which in this case you were given, okay? And be able to determine which ones are, how many of each you have, and you just take it to the math. And then multiply by 100, and that number, that all those percentages should add up close to 100%. If you're, at 99.99, no big deal. It's just a rounding error. A quick note about sig figs here. One of the challenges about sig figs in doing these type of calculations, and you may notice sometimes they roam around because you have an infinite number of sig figs, really. And so there's no right or wrong answer with respect to this type of calculation when it comes to sig figs, because none of these are measurements, okay? All of these are coming from the atomic weights, which are an infinite number of sig figs. And then we're multiplying by whole numbers, which are exact numbers. So we don't really have sig figs. So as a general guideline, as a general rule, just go to 2 decimal places, okay? Go to 0.01 decimal places, and you should be okay, okay? Let me repeat that. When you're doing the percent composition reactions, okay, don't be concerned about sig figs because you don't have sig figs there. All right, all these numbers have infinite number of sig figs, so do the calculations, and at the end, just go through. You're more than welcome to go through the 100, 2 decimal places, or 1 decimal place, whichever one. You wouldn't be incorrect to go one or the other. Okay, or round them up to the nearest whole number, all of them. Either one would be okay too. But this is only for these type of calculations. Simply because none of these are measurements, okay? They're measurements and it's a different ballgame. All right, so try these at home and we'll, we will go over them on Tuesday if we need to. But the question number one says, how many liters is 3.425 grams of carbon dioxide? Okay. And you should get an answer of 1.74 liters. Second question is, how many molecules are in 3.425 grams of carbon dioxide? Same amount of carbon dioxide. So now we're going to figure out how many molecules that corresponds to. And then you should end up with 4.68 times 10 to the 27 molecules. And then finally, if you have 3.0 times 10 to the 15 molecules of carbon dioxide, how much will they weigh? Okay. And you should end up with 2.2 times 10 to the -7 grams. See how tiny that number is? But you have a large, extremely large number of molecules. And that to me is what just mind boggles me with respect to our model of the atoms and how small these guys are. Extremely small. And imagine, if you will, all of the carbon dioxide on Earth. Imagine if you could figure how much that was, how many molecules you would be working with, how many individual molecules are there. A whole bunch. Okay, well, congratulations, folks. You are done with chapter 12. Okay. And like I said, bring those next Tuesday, the ones I just gave you. If you have want me to, we can go over it. If not, I will continue.